Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 2. Finite difference solution of linear two-point boundary value problems. The finite difference method is a powerful and widely used technique for numerically solving two-point boundary value problems. The method is relatively simple to understand and implement. The method involves discretizing the domain into a grid and approximating derivatives using difference formulas. It requires the domain to be discretized into a uniform grid, which simplifies the discretization process, especially when dealing with rectangular or linear problems. Finite difference method is highly efficient for solving linear two-point boundary value problems, especially when the ordinary differential equation has constant coefficients or simple functional forms. The objective of the finite difference method is to find an approximate solution to Yx that satisfies the ordinary differential equation and its boundary conditions through a discrete approximation. The steps of the finite difference solution are gridding, discretizing, implementing boundary conditions, constructing a linear system of equations, solving the linear system. We will illustrate the above steps for the generalized second-order two-point boundary value problem. Gridding or meshing is a process of constructing discrete points for which approximate solutions are sought. The solution interval is first divided into m uniform subintervals, and grid points or nodes are placed at the endpoints of every subinterval. The nodes are then enumerated, starting from either 0 or 1, and abscisses of the nodes are calculated from xi equals a plus ih, I equals 0 through m, but the corresponding ordinates, yi's, are the unknowns to be determined. Discretization is the process of transforming a continuous function satisfying an ordinary differential equation, as well as its boundary conditions, into a discrete function. An ordinary differential equation is discretized at a node xi, and the derivatives appearing in the ordinary differential equation, y prime, y double prime, and so on, are replaced by finite difference approximations. Consider the following two-point boundary value problem, which is satisfied for every x on from A to B. The ordinary differential equation for the ith nodal point, x equals xi, is expressed as follows, or in shorthand notation. To ensure a second-order global error, we replace derivatives with second-order finite difference formulas. Substituting the central difference formulas in the ordinary differential equation yields, and rearranging and collecting similar terms, we obtain the general difference equation. We define bi, di, ai, and gi to express this in much more simplified form. Difference equations for the unknown nodes are obtained by applying the general difference equation to yield the following specific difference equations. Where bi, ai, and di have prior definitions, this system has m plus 3 unknowns and m plus 1 equations. When the boundary nodes are imposed either Robin or Neumann boundary conditions, not only is the solution at the boundary node unknown, but it also results in fictitious nodes as well. In this case, the number of unknowns, including the fictitious nodes, becomes m plus 3, while the number of the actual nodes belonging to the physical system is m plus 1. We need to eliminate the fictitious nodes using the given boundary conditions. Implementing boundary conditions for a two-point boundary value problem is a process of applying conditions at specific points, i.e., the endpoints of the solution domain of the problem, in order to find a unique solution to the boundary value problem. These conditions help ensure that the solution is well-defined and matches physical or geometric constraints that are relevant to the problem. It is in this step where the fictitious nodes observed when the boundary is subjected to Neumann or Robin boundary conditions are eliminated. At the end of this stage, the number of unknowns and the number of equations are matched. If Dirichlet boundary conditions are imposed on both boundary points, ya equals uppercase A and yb equals uppercase B, then y0 and ym are known as uppercase A and B, respectively. The solutions for the interior nodes are always unknown. Substituting the known values into the difference equations of the boundary nodes, we get. Then, we carry the known terms to the right-hand side. Consequently, we obtain. If one or both boundary conditions are specified as either Neumann or Robin boundary condition, then the solutions of the boundary nodes, either y0 or ym or both, are unknowns. The discretization procedure creates additional unknowns due to emerging fictitious nodes, i.e., either y sub minus 1 or y sub m plus 1 or both. However, the boundary conditions provide additional difference equations to properly eliminate the fictitious nodes. The implementation of Neumann and Robin boundary conditions is essentially the same, in that Neumann boundary condition can be simply obtained by setting beta equals 0 in Robin boundary condition. When Neumann or Robin boundary conditions are applied on both boundaries, the number of equations or nodes is m plus 1, difference equations for I equals 0 through m, and the number of unknowns becomes m plus 3, y sub minus 1, through y sub m plus 1. We eliminate the emerging fictitious values y sub minus 1 and y sub m plus 1 using the boundary conditions. Consider the left boundary node, where the alpha 1ya plus beta, 1ya equals gamma, 1 boundary condition is subjected. The boundary condition is discretized as follows. The difference equation for the left boundary node also has y sub minus 1. Solving the discretized boundary equation for y sub minus 1, we get. We substitute y sub minus 1 into the difference equation for the left boundary node. Collecting the similar terms and simplifying, we obtain. Similarly, the difference equation for the right boundary node includes y sub m plus 1. Discretizing the right boundary condition, alpha 2, yb plus beta 2, yb equals gamma 2, and solving it for y sub m plus 1 gives. Substituting y sub m plus 1 into the difference equation for the right boundary node, collecting the similar terms, and simplifying yields the following equation. A unique system of linear equations is constructed whose size depends on the type of boundary conditions. Putting together the difference equations in matrix form, assuming Neumann or Robin boundary condition is employed on both boundaries, we obtain Ax equals R, where A and R are defined as. Note that the first and last row elements presented here are modified as follows due to implementing the boundary conditions and eliminating the fictitious node values. For the case with Dirichlet boundary condition imposed on both boundaries, the linear system, size m minus 1, can be expressed in matrix form as follows. The coefficient matrix is tridiagonal. The first and last rows remain unchanged, but only right-hand sides are modified as shown. Once a system of linear equations is constructed, the coefficient matrix and the RHS vector are established. The linear system is solved. The resulting system of equations for the two-point linear boundary value problems is typically a tridiagonal system, which can be efficiently solved by using the Thomas's algorithm. See section 2.10. Keep in mind that the accuracy of the numerical solution will improve as the interval size is reduced, i.e., h goes to 0. The two-point nonlinear boundary value problems also yield tridiagonal systems, but the solution procedure is iterative due to the presence of nonlinear terms. The advantages of the finite difference method are: it is very easy to discretize ordinary differential equations using the finite difference method. For a linear second-order boundary value problem, the finite difference procedure with the global error of order 2 results in a tridiagonal system of equations whose direct solution with the Thomas algorithm is fast and accurate. Accuracy of the numerical estimates improves as the interval size is refined, i.e., h becomes sufficiently small. The disadvantages of the finite difference method are: finite difference schemes of order of accuracy 3, 4, and so on are unreliable for the boundary value problems of conservative forms. The method is quite laborious to apply to non-uniform grids. When applied to 2D and 3D boundary value problems, it is generally limited to structured grids. That is all for now. See you next time with another topic. Bye.